Hello everyone, I am Dr. Belmont and today we're going to continue with the Organic Chemistry 2 course, and the topics that we're going to discuss today are nucleophilic addition to aldehydes and ketones, and particularly cyanohydrin formation. Okay, so let's jump to our board. Very well. So the general structure of aldehydes and ketones we have already discussed it briefly, right, in the past video, but we can have a short reminder on how the structures look like. So this would be something like a aldehyde, for example, and something like this would be a ketone, right? So we already know this structure, and we already saw last video that we can protect them, right? Because sometimes we will not want this partially positive charge to be available all the time, right? Sometimes we need to protect it from other nucleophiles, and the structure that we usually use might look something like this, right? The happy face that some of my students call. Give me a second. There you go. Okay. So that's for aldehyde, and for ketone would be something like this, right? Something like that. Well, you got the idea. Very well. And this is going to be useful if we want to protect from what? From any source of nucleophiles. And nucleophiles can be, for example, sp3 nitrogens. It can be, for example, carbanions in the form of Grignards, right? Right? These two lone pairs are quite negative. Or basically, for example, OHs, right? OH can also be a nucleophile sometimes. So when we want to protect them from the attack, right, what we do is that we use these protecting groups. But sometimes what we do want, right, is to attack them. And we're going to talk about a particularly important nucleophile that it's called cyanide. Okay, so what is cyanide? Well, cyanide actually is the conjugated base of an acid. Which acid? Cyanhydric acid, right? And cyanhydric acid has an equilibrium, if you put it into aqueous media, between H plus Cn negative, Cn minus. So we can consider cyanide as a type of carbanion, right? And what do you think is going to happen if, for example, I use this molecule, which is benzaldehyde, and I put it in the presence of cyanide, for example, like this. Well, I have a negative charge, very well, and it's going to attack what? The partial positive charge of the oxygen, very well. And what you will have in an equilibrium is something like this. With the lone pairs and the negative charge, very well. And if cyanide also, right, it's in equilibrium with what? With the cyanhydric acid, that means that we are going to have available, right, a proton that can be catched by the corresponding alkoxide, and what we will have, sorry, is something like this. Very well. So pretty cool, right? But there are a couple of observations that we need to keep on track with this, right? So let's try write down again the structure, and again the cyanide, and we would have something like this. And if you are observative enough, right, you can see that the carbon can be able to attack from the front, right, of the board, and give us something like this, right? attach here, and O negative attached there. Very well. Or it can also go and attack the other way, right? And in which this case what we would have is something different, and it would be like that. So now on the front what we're going to have is the alkylate. I'm going to erase this. The alkylate, and at the back the cyanide, right? So one would be what? The R, and the other one would be the S, and we have 50% chances to get either one or the other. And what we know like this is the racemic mixture. Right? So I'm going to ask you as an exercise, identify which of these ones is the R and which of these ones is the S. Very well. Why? Because right now what it attaches me is another type of reactions. So let's go ahead and rewrite what we have to do here. So I have my benzaldehyde, and I'm going to react this in the presence of HCN. So according to the mechanism that we already have discussed, what we will get is something like this, right? And right now I'm not going to give a lot of importance to the racemic mixture, right? There you go. And this molecule that you have here can be transformed through different pathways, right? Why? Because now the center, the reactive center, has changed. What we have here is an sp carbon, this one right here, and it's also going to be what? Partially positive. That means that we can react this with another nucleophile, right, to attack and transform the molecule. So let's go, for example, that maybe what I can do is that first I can react these with LiAlH4, so a source of hydrides. And then what I am going to add is a little bit of water. And the other possibility is that I can just directly react these with diluted acid. And this is going to give me, as a result, a amine. And this one is going to give me as a result a carboxilic acid. Very well. So let's go and jump to the next example, and let's see. So if I have this nitrile group, that's the name of this functional group, nitrile group. And theoretically speaking, what I add is a source of hydrides, right? What I will get is, well, basically a nucleophilic attack to what? Towards the carbon, which immediately will jump the electrons towards the nitrogen, and what we will have is something like this. Something negative, right? And for example, if we are using lithium aluminum, we're going to be available some lithium that is going to help us to stabilize the charge. Very well. But again, what I can do is to add, right, another LiAlH4, so I can have more sources of what? Of hydrides. And what is going to happen is that now, theoretically speaking, what I would get is something like this. I can have another hydride that will go attack and push forwards, right? So what we will have is something that is going to look pretty funny, but theoretically speaking, that's what we would get, right? I am proposing this structure. Why? Because lithium is in the same family as what? As hydrogen. So it's possible that we can create a stabilizing bond between the metal, in this case lithium, and nitrogen. And at the end, what I will do is that I will add a little bit of acid in water, and what I will get, right, it's, oh, so sorry, I forgot here an OH. Theoretically speaking, what I will get is something like this. Each of the hydrides that I add, each of the hydrides that I add, plus the nitrogen and the nitrogen attached to hydrogen. So what we end up is with a amine. Very well. And now on the next case, let's go and check what it could happen. Let me change some colors, right? And if I have my nitrile, like this one, right? And I add a little bit of acid in water, right? That was the other scenario that we would have. What do you think is going to happen? Well, remember that we need to perform a nucleophilic attack towards whom? Towards this carbon. So the best idea that we can get actually is that this nitrogen first gets protonated by the hydrogen. And what we will have is something like this. So I have my H, I have my OH, right? My carbon, my nitrogen attached to a hydrogen. And since this nitrogen has 4 bonds, it's going to be positive. So this is going to help a lot, what? For water. Right, with its lone pairs to go and attack the carbon. So what we're going to do now is to continue the movement of electrons. What I will get is something like this. Now the electrons are towards the nitrogen, and I have an oxygen attached to a hydrogen and attached to another hydrogen, and hence this is going to be what? Positive, right? With the other lone pairs. And I think that you already know what's going to be next. So oxygen doesn't like to be positive, so nitrogen is going to help and pick up one of the hydrogens of the oxygen, so we can get the next structure through an intermolecular reaction. Right, give me a second, let me make some space. Thank you very much. And what I will have is my carbon, right, bonded to OH, bonded to nitrogen, double bonded, very well, and this nitrogen is going to be positive. Very well. Now instead of changing the page, I'm going to erase this structure so I don't get lost. So I can continue in the upper part, right? Because the structure can get messy. So from here, what is going to happen is that these electrons are going to jump and are going to give the electrons now to the nitrogen. So the positive charge gets cancelled. And what I will get is something like this. So the OH stays as it is, the hydrogen stays as it is. My carbon, right, is going to be now double attached or double bonded to a oxygen, sorry, that is going to be positive. And now the carbon is going to be single bonded to a nitrogen, right, to a hydrogen, and to a hydrogen. Very well. And I think up to there, that's it. Very well. Yes, I think it is. And remember, since we were using an acid as a catalyst, that means that we have what? A conjugated base that is going to help us to pick up, right, the hydrogen of the oxygen, giving back the electrons to the oxygen, and what we will have is something like this. So we are closer, right, to reach what? The carboxylic acid that we're looking for, if you are observative enough to look at that. Right? So we have to do something with this amide, right? Because up to now what we have is it's an amide. So how are we going to solve that? Well, pretty simple. We're going to add more water. I'm going to change color just for fun. And I'm going to add more water, right? And also more acid. Remember that we have still that. So what's going to happen is that, again, the acid, right, it could be even the conjugated base that it's giving away this acid, it doesn't matter, right? Again, it's going to take away, right? Sorry, take in the proton. What we're going to have something like this. Again, the oxygen is positive, so it doesn't like to be positive, right? And the nitrogen here. And we still have what? Water. So I think that you already know what is going to happen. This one is going to attack this carbon, give the electrons towards what? The oxygen, right? And what we will have is something like this. Sorry, this one actually is positive, right? And the nitrogen is going to be like this. Very well. So if you're observative enough, what you will see is that this oxygen that is positive requires a little bit of help. Why? Because it doesn't like to be positive. And the nitrogen that it's pretty close to it is going to help you with a little bit of aid there, right? And what we will get is as follows. Very well, so let's change colors, now some red. Of course, positive, and another OH here. So as you can see, this structure looks a little bit crowded, right? It doesn't seem to be very stable, and absolutely you are right, because this nitrogen is already what? Positive, and it doesn't like to be like that. So we need to transform this into something a little bit more stable. So what about if one of these electrons, a pair of electrons, can just jump in and leave what? Ammonia as a leaving group. And what you will get is something like this. We will have the carbon that is going to be double bonded to an oxygen, single bonded to a hydrogen, right? And now with an OH like this, and you can see clearly that this resembles a lot what? The carboxylic acid. And at the end, what we will have is an NH3 that is going to help us to pick up the hydrogen and give back the electrons towards the oxygen. What we're going to get, right? Now it's something like this. Let's continue. It's going to be my final group, my hydrogen, my OH, and finally my carboxylic acid plus what? NH4 positive, and this positive charge is going to be balanced with the conjugated base of the acid, so everything worked well. Very well, thank you very much. This is going to be everything for this video, and I'll see you soon next time. Goodbye.